Today, we're diving into a really fascinating paper called ELLA, which stands for Efficient Lifelong LLM Adaptation. This work tackles one of the biggest headaches in AI right now. How do you get these massive models to keep learning new things without completely forgetting everything they knew before? It's a huge deal for making these models truly useful in the real world.
And this is really the million-dollar question, isn't it? If you just keep fine-tuning a model on task after task, you run smack into catastrophic forgetting. The other options, like replaying old data, are often just not practical because of the massive compute and storage costs, not to mention the privacy red flags. So the real challenge is finding that sweet spot, achieving plasticity to learn new things without sacrificing the stability of old knowledge.
So to really get why ELLA is such a clever approach, we first have to understand the existing landscape. Let's talk about the fundamental dilemma that most continual learning methods are stuck in. Right now, the field is pretty much caught between a rock and a hard place, with two dominant but flawed solutions. On one side, you've got strict orthogonality. Now, this works great for preventing forgetting. It basically forces every new task's updates into a completely separate mathematical space. But, it's a blunt instrument. It totally kills any chance for positive knowledge transfer between tasks, and over time, you just run out of room to learn anything new. On the other side, you have rehearsal or replay methods. And yeah, they perform really well, but they're often a logistical nightmare. We're talking impractical storage needs, massive compute costs, and of course, huge privacy concerns when you're constantly storing and reusing old data.
This is exactly where ELLA comes in and proposes a really elegant third path. The core idea isn't to forbid all interference between tasks, because some of it might actually be useful. The trick is to manage it selectively.
And this quote from the paper just nails the whole philosophy. ELLA's insight is that not all parameter overlap is created equal. The important, high-energy parts of a past update are what contain that crucial task-specific knowledge. But the low-energy directions, well, that's where the generalizable, transferable knowledge might live. So the goal is to penalize updates that try to mess with those high-energy directions while leaving the rest of the parameter space open for business.
This diagram gives us a great visual for how it works. You can see ELLA first aggregates all the previous low-rank updates into one matrix, which they call W_past. Then, when it's learning the new update, delta WT, it introduces a penalty that discourages this new update from aligning with the high magnitude, or high energy, directions of W_past. It's basically telling the new update, hey, see those important directions from past tasks? Yeah, stay out of there. Find another way.
So we have the high-level concept, which is super intuitive. Now let's pop the hood and look at how this is actually formalized into a mechanism that, by the way, comes with some pretty powerful theoretical guarantees.
And here's the beautiful part. At its heart, the mechanism is this surprisingly simple regularizer. It's just the squared Frobenius norm of the element-wise product of the current update and that aggregated matrix of past updates. This one simple term pushes the model to find update directions that have very little overlap with parameters that were really important for previous tasks. And the best part? It does this without needing to store all the individual adapters from the past. It's incredibly efficient.
So what does this penalty term actually do mathematically? Well, the authors prove in Proposition 1 that it acts as what they call an anisotropic shrinkage operator. It's a fancy term, but the idea is actually very intuitive. It means it selectively shrinks the parts of the update that are trying to go in the same direction as high-energy past updates, while leaving the coordinates that had low energy in the past relatively untouched, free for knowledge transfer.
And this is what really elevates the whole approach. This isn't just a clever heuristic that seems to work, it's mathematically principled. The paper includes a proof that this mechanism provides a formal upper bound on the amount of interference with past tasks. That guarantee of controlling forgetting is a huge step forward.
All right, the theory is elegant, no doubt. But the real question is, how does it perform in practice? Let's take a look at the benchmark results.
And the numbers really do speak for themselves. Across 3 major continual learning benchmarks, ELLA consistently establishes a new state-of-the-art for replay-free methods. But here's the truly remarkable part. On 2 of these benchmarks, it actually outperforms data, which is a strong baseline that uses data replay. Think about that. ELLA is achieving better performance without the cost, storage, and privacy headaches of rehearsal.
This chart really gets to the heart of why ELLA is so much better. We're looking at a metric called forward transfer, or FWT. Basically, it asks, does learning old tasks help you learn new tasks? For methods like OLORA, you can see the answer is no. It has negative transfer. It actually makes future learning harder.
But Ella is the only method here that achieves positive forward transfer. Learning the past actually helps it learn the future more effectively.
These radar plots are another fantastic way to see the difference. Each point on the chart is a different task in a long sequence. You want to see a nice, big, stable shape, and that's exactly what you get with Ella, in red. It maintains consistently high performance across the board. The other methods, you see these huge dips and valleys. That's catastrophic forgetting in action. Ella's performance is just way more robust and well-rounded.
Okay, so it's a top performer on the tasks it's seen. But honestly, that's only half the story. Two of the most compelling advantages of Ella are its ability to generalize to completely new things and its incredible efficiency. Now, this number right here might be the single most important result in the entire paper. This is delta GA. It's a metric that measures how the model's core zero-shot generalization ability changes after it's gone through all that continual learning. A negative number here is bad. It means the model got dumber. And that's the punchline. Ella is the only method they tested that showed a positive delta GA. Let that sink in for a second. This means the process of continual learning with Ella doesn't just avoid catastrophic forgetting, it actually improves the model's fundamental ability to generalize to tasks it's never seen before. It's not just maintaining knowledge, it's building constructive, cumulative intelligence. And then there's the efficiency, which is just staggering. Let's run through these quickly. Compared to a replay-based method like data, Ella has a 35 times smaller memory footprint.
The amount of data replay it requires? 0. Absolutely none. That is a massive win for privacy, for storage, and for compute.
And the total storage overhead per task is just a little over 4 megabytes. This makes Ella an incredibly practical and scalable solution for long-term, real-world continual learning.
Okay, so let's zoom out for a second and tie all of this together. What's the big picture takeaway from this work?
So to recap, Ella delivers a new state-of-the-art for replay-free continual learning. It finds that perfect balance between stability and plasticity using its clever selective decorrelation method. Critically, it goes beyond just preventing forgetting and actually enhances the model's generalization to brand new tasks. And it does all of this in a framework that is incredibly efficient and scalable. It really does tick all the boxes.
You know, what's so exciting about this paper is that it really feels like it shifts the conversation. For so long, we've been focused on just mitigating a problem, on stopping catastrophic forgetting. Ella points towards something much more profound, a future of constructive, cumulative learning. And it leaves us with this really powerful question to think about. If our AI systems can learn continuously, efficiently, and actually get smarter with every new experience, what new possibilities does that unlock for the future?